Hi students, in the last class we have discussed about finite wavelength effect, and we have discussed about what is input quantization error, what is product quantization error, and what is coefficient quantization error. In that we have discussed about truncation error, and now we will discuss it about the round off error. Okay, so here the round off error involve only the magnitude and it is independent of the type of fixed point. Okay, so here the normally the rounding error ranges from similar to that of this. Here it ranges from e power minus b minus 2 power minus l divided by 2. This is for negative peak and this is for positive peak, but here we are not going to concentrate on l because l is the that is the input length. Okay, here we are not going to bother about what is the length of the input bit, just we are going to consider only the bit truncating bit. Okay, so here I am truncate that is because it is independent of this point, fixed point. Okay, so just I am going to consider this minus 2 power minus b by 2 to 2 power minus b by 2. Okay, so this is what the rounding error for both sine magnitude and its 2's complement. So this is what the quantization error diagram. Sorry, this is what the truncate that is the round of error diagram. Here it is lies between 2 power minus b by 2, right? 2 power minus b by 2. Here is the positive peak 2 power minus b by 2, negative peak is minus 2 power minus b by 2. As you know what is step size in quantization error, so you have studied this in digital communication. So this is what the round of error for sine magnitude and 2's complement representation. Next topic is quantization effects in analog and digital conversion of signal or input quantization error. So we know that for in A to D conversion there are three steps involved in it. First one is sampling, second one is quantization, and third one is encoding. Okay, third one is encoding. So we know that this sampling perform the continuous time signal, that is it sample the continuous time signal at a rate much greater than the Nyquist rate, and it will convert the continuous time signal into a discrete time signal using the Nyquist rate condition. And quantizing the amplitude of the signal, this quantization is nothing but we are quantizing the amplitude of the signal into the set of discrete level, that is we are going to quantize the levels, input levels, quantize the levels, then finally we will perform encoding. But here we are going to concentrate on what the error happened due to this quantization. Okay, so consider a quantizer. Here consider a quantizer. So when you are giving an input, so after the quantization, the output of the quantizer is xq of n. But here what will happen is there will be a quantization error due to the truncation or rounding process. So here we are with that quantization error is known as E of n here. This is known as the quantization error, which is nothing but xq of n minus x of n. So here x of n, so in this you will have a summer. So here you will get an quantization error E of n. So this xq of n is nothing but this x of n, this plus this quantization error. Okay, since the rounding involved in this process, we are not going to perform truncation, so we are going to perform rounding. Yes, so so consider this is your input signal. So I am going to sample this signal at particular time instance by request rate. So after that sampling I will get this samples. So now consider here it is 1.4, here it is 2.6. so like that you will have different values. So what I will do is I will perform quantization by rounding it. So here I will make it to 1 and this I will make it to 3. So due to this rounding you will get some error. Okay, so that is said to be an quantization error. Since the process involved is rounding, here that is minus b to 2 less than E of n, that is the quantization error, less than 2 power minus b to 2. So this is what the range, right? So that I have written here. So this lies between this range. Okay, so this quantization error, what are the assumption we are going to make is this quantization error is you said to be uniformly distributed over this range, distributed distributed over this range. So in this range, this error is uniformly distributed. It is also assumed that this quantization noise is a white noise sequence, and it is uncorrelated with the input signal, Okay, so first one is it is uniformly distributed over this range. It is also assumed that it is a white noise sequence and it is uncorrelated with the input signals. These assumptions are valid if the quantization step size is small. So this will be valid when we are having this quantization step size as small. Okay, so small, the signal x of n traverse several quantization level between these two successive samples. So now in order to understand this input quantization errors, we are going to consider a signal to noise ratio have to be evaluated to quantify the effect of additive noise. So here I am going to take signal to noise ratio as 10 log of p x of n by p e of n. Okay, so this is what the signal to noise ratio. This is the signal power. So signal power, so this is what your quantized noise power. Okay, now the probability density function for this lies between, that is 2 power minus b by 2, 2 power minus b by 2. So here the magnitude is 2b. Okay, so this is probability of error. Here we are going to assume that this lies in the range 2 power minus b by 2 to plus 2 power minus b by 2, and here and the magnitude of this is 2 power b. Okay, now here I am going to find out the quantization noise power. Okay, so here this is denoted by sigma e square. So and here in order to find this probably, that is the quantization error, so here we have to take e, that is the error. Okay, the error square into probability of that error. Okay, so and the limit is this range minus b minus 2 minus b by 2 to minus b by 2. So this is the formula we need to take it for calculating the quantized noise power. And for substituting these values, so minus 2 power minus b2 by b by 2, 2 power minus b by 2, here the e square, here you will have as such, here probability of this is 2 power b into dE, or consider this as epsilon, you will have this as epsilon. Okay, so here it is 2 power b integral minus 2 minus b by 2, 2 power minus b by 2. Here I need to differentiate this. Okay, so I need to differentiate this. So what I will get is 2 power b, so epsilon cube by 3, and the range is from 2 power minus b by 2. Sorry, this is what here, right? This is what here, right? So minus 2 power minus b by 2, not for that b by 2, by b by 2. So here 2 power minus b by 2. So this can be written as 2 power b e power 3, the epsilon 3 by 3 into 2 power minus b. So this 2 power minus b by 2 can be written as 2 power b 2 power minus 1, right? So 2 power minus b minus 1, I can write this. So this can be written as 2 power minus b minus 1, 2 power minus b minus 1. So this is of negative amplitude. So this is negative amplitude. So I hope this is what divided by 2. So now substitute these values. So what you will get is, so here 2 power b by 3. So 2 power minus b minus 1 minus 2 power, already minus is there, so it will become plus. So So here it is cube, right? So cube 2 power minus b minus 1 the whole cube divided by 3. Okay, now simplify, you need to simplify this. So when you apply the limit, you will get 2 power minus b minus 1 3 whole power 3 minus 2b minus 1 the whole power 3. So when you simplify this, what you will get is, you will get 12 e power, which is equal to 12 into 2 e power minus 2b. So this is what your now quantization noise power PE of n. So now we need to write the signal to noise ratio. The signal to noise ratio SNR is equal to 10 log of Px of n by Pe of n. Okay, so this can be represented as 10 log of Px of n. Okay, so here now if it is in denominator, if it is in division, you can write it in if it is in division, you can write it in subtraction, right? Similarly, I am going to represent this Px of Pe of n. I'm going to represent this in after substituting these values, I'm going to write this equation. So here after simplification, so SNR is equal to 10 log 10 PXN plus 10.8 plus 6b. So here what we can conclude is, here in this input quantization noise power, each additional bit accommodate in the quantization process reduces the quantization noise power by 6 dB. Okay, so this is what the signal to noise ratio of the input quantization error or analog to digital conversion of the signal. The next one is the steady state output noise power. We are going to calculate for the output noise. Okay, so here considered a system. So this is the quantized input is given to this system. So you will get some output y of n. Now we are going to discuss only about the noise. The input to this system is E of n. Okay, E of this is considered, this is small e and capital E. Okay, so therefore output is convolution of E of n into H of n. So this is the convolutional formula. Now here if you want to find out if it is noise, what you will do, you will find out the variance, right? Because the mean is here what we have assumed that here it is uniformly distributed, right? So here we need to find only the variance. Okay, so here sigma E square into H square of n, where this output noise power sigma square E of n is equal to input noise power into this summation n is equal to 0 to infinity H square of n, the power of this one. Okay, so now by using Parseval's theorem, either you can use this formula or you can find it from a Z domain. Okay, so this is what the formula for a steady state output noise power. Now consider the problem. Find the steady state variance of the noise in the output due to the quantization of the input for the first order filter. Okay. Now here if you want to find the quantization noise output power, so you need to evaluate this formula, that is summation n is equal to 0 to infinity H square of n. Okay. So here we need to first find sigma E square and we need to find H square of n. So here if you want to find H of n, we from the given equation, so here consider the first y of n equal to a into y of n minus 1 plus x of n. Here we may not able to find directly H of n. So first we need to find H of z by applying z transform, by taking z transform. So this become H of y of z, a into y of z, z power minus 1 into x of z. So y of z 1 minus a z inverse equal to x of z. So H of z is equal to y of z by x of z, which is equal to 1 by 1 minus a z inverse. So here if it is a n u of n, the z transform is 1 minus a z inverse. So here the h of n is equal to a n into u of n. Okay, so this is the resultant for this. And now here we need to find this sigma e square. Sigma e square nothing but we have find out the input quantization noise power is equal to 2 power minus 2b by 12. So from this sigma square epsilon of n, we can find it from 2 power minus 2b by 12. Substituting in this equation, summation, here it is that is in here k, here n is equal to 0 to infinity. What is h of n? H of n is a power n into u of n the whole square. Okay, so here 2 power minus 2b by 12 summation k n is equal to 0 to infinity a square to n. Okay, here u of n is 1, right? Okay, so summation n is equal to 0 to infinity a power n, formula is 1 by 1 minus a. Okay, so substituting in 2 power minus 2b by 12, 1 instead of a, what I am having here, it is I am having a square, so here 1 minus a square. So this is what the quantization steady state, that is steady state variance of the output noise. Now see this problem, the input to the system is they have given one difference equation is applied to an ADC. What is the power produced by the quantization noise as the output if the input is quantized to 18 bits and 8 bits and 16 bits. Okay, so now here if you want to find out the quantization output noise pair, we know this is the formula, sigma e square equal to sigma input noise power into summation n is equal to 0 to infinity h square of n. So this is the formula. Now here we need to find h square of n. Sigma e square is constant, he 2 power minus 2b by 12 for all problem, it varies only on the number of bits. Okay, now find out sigma epsilon, that is e square, sigma e square into, if you want to find h square, you need to first simplify this y of n. So y of n is equal to 0.99 y of n minus 1 plus x of n by taking z transform. Y of z is equal to 0.999 y of z power minus 1 plus x of z. So y of z 1 minus 0.999 z inverse equal to x of z. So here h of z is equal to y of z by x of z, which is equal to 1 by 1 minus 0.99 z inverse. So your h of n taking inverse, so this is nothing but 1 minus a z inverse is nothing but transform is u of n a of n. So here 0.999 n into u of n. So this is the inverse z transform result. Now first thing here we are going to find out for 8 bits. So sigma square epsilon is equal to 2 power minus 2 into 8 divided by 12 into summation n is equal to 0 to infinity. So 0.999 whole square. So substituting after simplifying this, so first considered for 8 bits, so 8 bits sigma e square, the same thing here, the formula you will get here, this one as u h of n into a u of n the whole square here. So 1 minus similar to previous problem, so I got this equation. Now do it for 6 that is 16 bits. So what you get, 2 power minus 32 divided by 12. So here one change, summation n is equal to 0 to infinity 0.999 the whole square. So here 2 power minus 32 by 12, 1 by 1 minus 0.99 the whole square. So simplify and find out the answer. And also I will given another problem. So here consider x of n and e of n is given. So this is what your y of n. So z inverse So this is multiplied by 0.8 and is given to the system. So now you need to find out output variance sigma square E of n for this system. Okay. So first to find, listen, don't confuse with the E of n. E of n is the noise produced in this introduced due to this quantization effect. So here first write down the y of n equation. So what you will get, the y of n equation is x of n plus 0.8 y of n minus 1 from this. Then you know how to proceed it, right? So you have to proceed for 8 bits. Okay, have to proceed for 8 bits, and we have to find out this sigma squared E epsilon of n. Okay, so we will discuss the answer in the next class. You just try these two problems and we will discuss the answer. Hope you have understand this input quantization noise power and output quantization noise power. Thank you.